Hello, I'm Grzegorz Dudek from Częstochowa University of Technology, Poland. I would like to present a new method of time series decomposition called STD, Seasonal-Trend-Dispersion Decomposition. First, motivation and contribution of this work. Then I'll show existing methods of decomposition. I'll present the proposed decomposition in two versions. Then I'll show some examples of time series analysis using the proposed method. I'll show how this method can facilitate forecasting complex time series, and I conclude this work. Time series analysis and forecasting is an extremely important task in many fields, including business, finance and economy, industry, government, politics, health, and so on. However, this task can be difficult due to the complex nature of the time series. Time series can exhibit a variety of unobservable latent components that can be associated with different types of temporal variations. These include a long-term tendency or trend, cyclic or movements superimposed upon the long-term trend, usually non-periodical, seasonal variations, periodical, and irregular fluctuations. Structural time series decomposition, which involves decomposing a series into components having a direct interpretation, is very useful from a practical point of view. In recent years, many methods of time series decomposition have been developed, which extract and reveal different time series properties. Unfortunately, they neglect a very important property, that is time series variance. To deal with heteroscedasticity in time series, the method proposed in this work, a seasonal-trend-dispersion decomposition, extracts the trend, seasonal component and component related to the dispersion of the time series. We define STD decomposition in two ways, with and without an irregular component. Time series decomposition has a long history dating back to the mid-19th century. A structural model is formulated directly in terms of unobserved components such as the trend, cycles, seasonals, and remaining component. Trend and cycle are usually combined in one component called the trend for simplicity. These components can be combined in two ways, additively or multiplicatively. In these equations, Y denotes the observed series, T is a trend cycle component combining the trend and cycle, S is the seasonal component, and R is the irregular component or remainder. An additive decomposition is applied if the variation around the trend cycle or the magnitude of seasonal variations doesn't change with the time series level. When such variation is observed to be proportional to the time series level, multiplicative decomposition is more appropriate. But this is where the question arises. What if the variation is not proportional to the level? Our proposed method tries to deal with this problem. Now, without going into details, I will show the results of time series decomposition using standard methods. We will use as an example time series expressing monthly electricity demand for Poland from 1997 to 2014. Note that the time series has decreasing variations with the trend level. In the additive model, heteroscedasticity in time series has to be expressed by heteroscedasticity in one or more decomposition products. Usually the trend is a smoothed original time series, so it doesn't include short-term variations of varying variance. These variations appear in the seasonal and irregular components. If the decomposition method produces a regular seasonal component that is composed of seasonal cycles of the same shape, which is a classical approach, the time series variance has to be expressed by the irregular component. But a desired property of the irregular component, which is often assumed for inferential purposes, is to be normally identically distributed and not correlated, which implies independence. When the variance of the irregular component changes in time, it doesn't express white noise in the strict sense. Therefore, the additive model is not recommended for heteroscedastic time series. The two panels on the right show the mean value of the component and its standard deviation over the following seasonal periods, the 12-month periods in our case. Notice how the standard deviations of the trend and reminder components change over time. In the multiplicative model, all components are multiplied, so the variations included in the irregular and seasonal components are amplified or weakened by the trend. An increasing trend increases these variations, while a decreasing trend decreases them. Thus, the multiplicative model is most useful when the variation in time series is proportional to the level of the series expressed by the trend. Seasonal and trend decomposition using LOS is one of the most popular decomposition methods. It produces a smoother trend than classical decomposition methods I've just presented, due to the use of local polynomial regression called LOS. The seasonal component in STL is allowed to change over time. It averages the real seasonal patterns, but can still reflect its amplitude. Therefore, to compensate for the amplitude mismatch, the irregular component may be smaller than in classical decomposition methods. However, it still expresses the variable variance and autocorrelation. Another popular method of additive time series decomposition uses a discrete wavelet transform. Wavelet-based multi-resolution analysis decomposes the series into an iterative process into components with decreasing frequencies. A low-frequency component, the so-called approximation, represents the trend, and high-frequency component, the so-called details, represent the detailed features of the time series. Each of them expresses changing variance. The decomposition depends on the form and parameters of the wavelet function, which is a function of both time and frequency. Empirical mode decomposition decomposes the time series in the time domain into components called intrinsic mode functions, IMFs. They form a complete and nearly orthogonal basis for the original time series. An IMF amplitude and frequency can vary with time. The IMFs extracted at subsequent levels are characterized by ever lower frequencies. The variance of the series is distributed between components. Our method, STD, produces three components: seasonal component, trend, and dispersion component. The seasonal component reflects seasonal patterns, preserving their shapes. The patterns are normalized. They have the same mean and variance. The trend reflects the level of the series in the successive seasonal periods, 12 months in this case, while dispersion component reflects the local variability of the time series, that is, variability in the successive seasonal periods. Note that standard deviation of all components in each seasonal period doesn't change. The local variation is expressed by a separate component, dispersion component. And now more details on how the STD components are extracted. Let yt be a time series with a seasonality of period n. Assume that the length of the series is a multiple of the seasonal period. If not, we can shorten the series removing a few elements from the beginning or the end. Time series can be written as a series of successive seasonal sequences. This is a sequence of the first seasonal period, and this is the sequence of the last kth seasonal period. The average value of the ith seasonal sequence is as follows, and the diversity of this sequence is defined as follows. Now we define the trend component using averages of the successive seasonal sequences, and the dispersion component using diversities of these sequences. Based on the trend and dispersion components, we define the seasonal component as follows. We subtract the trend, average values of the seasonal sequences, from the time series and divide the result by the dispersion. We can express STD decomposition as follows. Note that the trend and dispersion components are step functions, where the step length corresponds to the seasonal period n. The trend expresses the level of the time series in successive seasonal periods, while the dispersion expresses the variation of the time series in these periods. The seasonal component is composed of the seasonal patterns, which are centered, that is, the average value is 0, and unified in variance, that is, the dispersion is the same. Moreover, when we express seasonal patterns by vectors of n components, their length is equal to 1. Thus, they are normalized vectors. Although unified, the seasonal patterns differ in shape. The shapes express unified variations of the series in the successive seasonal periods. Note that the shapes are not smoothed or averaged as in the standard decomposition methods. A variant of STD is STD with a remainder component, STDR. In STDR, the trend and dispersion components are defined in the same way as in STD. The seasonal component is defined using an average seasonal pattern determined as follows. The seasonal component in STDR is a sequence of k averaged seasonal patterns. Thus, it is identical across all seasonal periods. The remainder component is calculated from this equation. STDR decomposition is expressed as follows. Note the same trend and dispersion components as for STD and the different seasonal component, which for STDR is composed of the same averaged seasonal pattern. The remainder corresponds to the mismatch between the original seasonal cycles and the average seasonal cycles. Thus, it contains additional dispersion resulting from averaging the seasonal cycles. This dispersion is lower for the cycles whose patterns are similar to the averaged pattern. Note that the remainder has a zero average value in each seasonal period. To assess stationarity of the remainder visually, this figure shows the plots of its sample autocorrelation function and sample partial autocorrelation function. As can be seen from this figure, most of the spikes are not statistically significant. That is, the remainder series is not highly correlated, which characterizes a stationary process. To confirm that the remainder is stationary, we apply three formal tests for a unit root in a univariate time series. Augmented Dicke-Fuller test, Kwiatkowski-Phillips-Schmidt and Shin test, and Phillips-Perron test. All tests confirmed a stationarity at a 1% level of significance. And now some examples of decomposition of different time series. As a first example, we use the classic Box-Jenkins airline data, that is monthly totals of international airline passengers from 1949 to 1960. This time series expresses an increasing trend and strong yearly periodicity, n is equal to 12, that increases in size with the time series level. The figure shows both STD and STDR decompositions. They have the same trend and dispersion components. The seasonal component for STD is shown in blue, while the seasonal component for STDR as well as the remainder component are shown in red. Note that the seasonal patterns generated by STD are very similar in shape. The second example uses data from the US unemployment rate for males, observed from January 1992 to December 2013. The seasonal patterns are similar in shape, except for three patterns, which reflect sharp spikes in unemployment in the final months of the year. Due to a deviation from the typical shape for these three sequences, the remainder takes larger values for them than for other annual sequences. Nevertheless, it passes the stationarity tests. The third example concerns hourly electricity demand. Time series of this type exhibit triple seasonality: yearly, weekly, and daily. The figure shows decomposition products of the hourly electricity demand for Poland in 2018. We assumed a seasonal period as a daily one, n is 24. We show three weekly sequences of the time series from January, July, and December. As can be seen from this figure, the seasonal component expresses daily patterns whose shapes are related to the day of the week and the season of the year. Note that the trend and dispersion components have both weekly and yearly seasonalities. These two components can be further decomposed using STD or STDR. The remainder passes all the stationarity tests. The next two examples are for financial time series. We analyze one of the most important stock market indexes, S&P 500. This index shows development within a rising trend that dips at the beginning of 2020 due to the COVID-19 crisis. The time series doesn't express seasonality. We assume n as 16 weeks for decomposition. Because of the rising trend, the 16-week patterns forming the seasonal component have a rising character, but differ due to the significant random noise. For the pattern representing the COVID-19 4 period, the highest remainder values are observed, as well as the highest dispersion. The remainder passes all stationarity tests. This figure shows decomposition of the S&P 500 returns. While the original time series of S&P 500 index is non-stationary, the returns fluctuate around a stable mean level. However, the variability around the mean changes. In the period 2019-2021, it is highest during the COVID-19 crisis. The remainder passes all the stationarity tests. The last example concerns decomposition of a synthetic time series, a Mackey glass time series which is produced by the delay differential equation. With the assumed parameters, the time series is chaotic and exhibits cyclic behavior. We assume the seasonal pattern length as 51. Note the irregular character of the seasonal patterns and also the chaotic variability in the trend and dispersion components. The remainder passes all the stationarity tests. Decomposition not only helps to improve understanding of the time series, but it can also be used to facilitate forecasting complex series. Extracted components have lower complexity than the original time series and can be modeled independently using simple models. In the case of STDR, the seasonal pattern doesn't change and we can use a naive approach to predict it for the next period. It is just copied for the next period. In STD, the seasonal pattern changes and we should use an appropriate forecasting method to predict it. Note that in the examples considered above, the remainder was a stationary process. Thus, it can be predicted even by those methods that require stationarity, such as ARMA. To avoid the troublesome task of forecasting all the components, we can use alternative approach. We can combine the components into input and output patterns. The forecasting model predicts output patterns based on the input patterns, which are seasonal patterns expressed by vectors as I, where yi is a vector representing the ith seasonal sequence of the time series. Thus, the input patterns are centered and normalized seasonal sequences, such as those produced by STD. The output pattern represents a forecasted seasonal period. It is defined as follows. Tau is a forecast horizon. Note that to calculate the output pattern, we use the average dispersion for sequence I and not for sequence I plus tau. This is because these two coding variables for future sequence I plus tau, which has been just forecasted, are not known. Using the coding variables for the previous period has consequences. The output patterns are no longer centered and normalized vectors like the input patterns are. But if the mean value of the series and its dispersion don't change significantly in the short period, the output patterns are close to centered and normalized. The forecasting model fits function f and produces the prediction of output pattern. This pattern is post-processed to obtain the real forecasted sequence using transform equation for output pattern definition. Note that in this equation the coding variables for mean and dispersion are known from the most recent history. This enables us to perform the post-processing, decoding. Note that the equations for input and output patterns filter out the current process variability from the data. That is, filter out the local average and dispersion. The model learns on filtered, unified patterns and forecasts output pattern. This equation introduces information about the process variability in sequence I, the most recent historical sequence, into the output data. This approach enables us to take into account the local variability of the process when constructing the forecast. Due to a representation of the time series by unified patterns, the forecasting problem simplifies and can be solved using simpler models. This figure shows forecasting based on patterns with similarity-based methods. Input patterns are denoted by X, and output patterns are denoted by Y. In the first stage, we preprocess the time series into patterns. Then we select the most similar input patterns from history to the query pattern, that is last pattern, the pattern directly preceding the forecasted period. We also calculate the weights depending on the similarity level. In the next step, we aggregate Y patterns paired with X patterns, that is representing sequences I plus tau, weighting them. As a result, we get the forecasted Y pattern. Then we decode this pattern and have the forecast of the time series for the next period. So the idea is simple and clear. In these works, we can find details of forecasting models based on patterns. These ones use a similarity-based approach. This one uses linear regression models. This two uses regression trees and random forest. This uses classical neural networks. This randomized neural networks. This uses hybrid model combining exponential smoothing and recurrent neural network. And this one uses artificial immune systems. The proposed decomposition method can be summarized as follows. It distinguishes itself from existing methods in that it extracts the dispersion component, which expresses the short-term variability of the time series. A separate dispersion component is very useful for heteroscedastic time series analysis. It has no parameters to adjust for seasonal time series. For non-seasonal time series, only one parameter should be selected. In STD, a seasonal component is composed of centered and normalized seasonal patterns, which express the shapes of the seasonal cycles. By emphasizing these shapes, STD facilitates comparison analysis of the seasonal cycles. In STDR, a reminder component expresses the difference between the real seasonal cycles and the averaged cycles. It enables the detection of outlier seasonal cycles that differ in shape from the average cycles. The algorithms of STD and STDR are very simple and easy to implement. The computational time is extremely fast. STD can be used for encoding the input and output variables for the forecasting models. STD-based encoding simplifies the relationships between variables, which translates into simpler models and can improve forecasting accuracy. The details of the method can be found in this paper. Thank you very much for your attention.